Hello everybody, I'm Abul and in this video I'm going to explain the hybridization in chemistry from a simple point of view. First, it is necessary to take a look at the images of spherical s orbitals and dumbbell-shaped px, py, and pz orbitals. As can be seen, the px, py, and pz orbitals are orthogonal to each other, and assuming the participation of the s and p orbitals of the nitrogen atoms in the formation of ammonia, if 3 unpaired electrons in p orbitals overlaps with the 3 hydrogen, we would expect the formation of ammonia with bond angles of 90 degrees. But in reality, this is not the case, and nitrogen atomic orbitals form the most common and stable bonding arrangement, which include 3 sigma bonds in a triangle pyramidal geometry with bond angles of 107 degrees. Other similar molecules such as BH3 with a bond angle of 120 degrees, CH4 with the bond angles of 109.5 degrees, and H2O with the bond angles of 105.5 degrees can be named. To explain such facts, Linus Pauling proposed that the valence atomic orbitals in a molecule are different from those in isolated atoms. In fact, atoms mathematically mix their valence atomic orbitals and create new orbitals, which are called hybrid orbitals. To hybridize 2 atomic orbitals, we consider the mathematical combination of atomic orbitals and draw new hybrid orbitals considering constructive and destructive interference. Here I wanted to show the hybridization process for sp hybrid orbitals as a result of the mathematical combination of 2 s and pz orbitals, and during the constructive and destructive interference, 2 sp hybrid orbitals are obtained in the dumbbell shaped with 1 large loop and 1 small loop which are oriented along the z-axis. The energy of hybrid orbitals is equal to the average energy of mixed orbitals. In the other example, I wanted to show the hybridization of pz and dz square orbitals. As can be seen, the pz and dz square orbitals are combined mathematically, and by the constructive and destructive interference, 2 pd hybrid orbitals are obtained in the dumbbell shaped, which are oriented along the z-axis. And so the energy of pd hybrid orbitals is equal to the average energy of mixed orbitals. Then here we can mention 4 important points in the hybridization. Hybrid orbitals are due to the mathematical combination of atomic orbitals. You can see here the mathematical combination of s and p orbitals in the left side and p and d orbitals in the right side. The equality of the number of atomic orbitals participating in the hybridization with the created hybrid orbitals. You can see here that from the combination of 2 atomic s and p orbitals, 2 hybrid orbitals achieved. The type of obtained hybrid orbitals varies with the types of atomic orbitals mixed. For example, sp obtained from mixing of 1 s and 1 p orbitals, and sp2 obtained from mixing of 1 s and 2 p orbitals. And finally, the energy of hybrid orbitals are average of the energy of mixed atomic orbitals. How the hybridization is involved in the stability of the molecule. Why do atoms in the molecular structure need hybridization? With the comparing of the orbital expansion between the hybrid orbitals and the isolated atomic orbitals, we can easily see that the hybridization causes to extend the electron density in the bonding direction. Also, this orbital expansion minimizes the repulsion between the electrons that occupy them in the bond making. On the other hand, according to the valence bond theory and valence shell electron pair repulsion theory, chemical bonds like to have an angle higher than 90 degrees to become more stable. Therefore, the mixing of a spherical s orbital with p orbitals makes it possible to increase the bond angle and the molecule can adopt its most stable form. In the table below, it can be seen that by using the Drago rule, the angle of hybrid orbitals increases with the increase in the percentage of s orbital in the hybridization. Here I wanted to find the bond angle of sp2 hybridization. We must use the 33 instead of percent of s in the Drago rule. Then cosinus theta equal minus 0.5 and finally the theta obtains 120 degrees. Now I wanted to show the 5 common types of hybridization as sp with linear geometric with 180 degree bond angle, sp2 with trigonal planar geometric with 120 degrees bond angle, sp3 with tetrahedron geometric and 109.5 degree bond angle, sp3d with trigonal bipyramid geometric and 120 degree and 90 degree bond angle, and finally sp3d2 with octahedron geometric with 90 degree bond angle. To investigate the hybridization of beryllium atom in a beryllium Cl2 molecule, it is necessary to consider the electronic configuration of isolated beryllium atom with 2s2 and 3 empty 2 orbitals. Regarding to the valence bond theory, to form the BeCl2 molecule, we need 2 orbitals with the single electron of central atom. Therefore, as a result of excitation, an electron is transferred from 2s orbital to the 2p orbitals of beryllium. In the following, hybridization of 2 non-equivalent s and pz orbitals of beryllium gives rise to 2 equivalent sp hybrid orbitals with single electron that lie 180 degrees apart. Note that the orientation of hybrid orbitals are in z-axis and the other 2 px and py orbitals are empty and intact and are placed on the beryllium without participating in the hybridization. Finally, two chlorine atoms share their single electron p orbitals to making bond with two hybrid orbitals of beryllium and form the BeCl2 molecule. We can find similar compounds with the same sp hybridization, such as the carbon in acetylene, carbon dioxide, and thiocyanate ions. sp2 hybridization. Now I wanted to examine boron hybridization in BH3 molecule. For the isolated boron atom, we see the 2s orbital with an electron pair and one of the 2p orbitals with single electron. Regarding to the valence bond theory, to form the BH3 molecule, we need 3 orbitals with a single electron of boron atoms. Firstly, as a result of excitation, 1 electron is transferred from 2s to one of the empty 2p orbitals of boron atom. In the following, the hybridization of 3 non-equivalent 2s, 2px, and 2py orbitals of boron give rise to 3 equivalent sp2 hybrid orbitals with single electron that lie 120 degrees apart that point toward the vertices of an equilateral triangle with the 2pz unhybridized orbital that perpendicular to the triangle plane. Each sp2 orbitals overlaps with s orbital of hydrogen with single electron to make a BH3 molecule. We can find similar compounds with the same sp2 hybridization, such as the CH3 plus, NO3 minus, CO3 2 minus, carbon in ethylene, and central oxygen in O3. sp3 hybridization. Carbon hybridization in methane molecule is the good example for the sp3 hybridization. With considering in carbon electron configuration, we can see 2s orbital with an electron pair and 2 of the 2p orbitals with single electron. Then for the formation of CH4, the carbon will lead to excitation, and 1 electron of 2s orbitals is excited to empty 2p orbitals. In the following, 1s and all 3p orbitals of the carbon mix together and form the 4 sp3 hybrid orbitals, which point toward the vertices of the tetrahedron with 109.5 degrees. The following, each sp3 orbitals overlaps with a hydrogen atom to form the methane molecule. We can see the similar compounds with the same sp3 hybridization, such as the NH4 plus, PCl4 plus, and SiF4. Is excitation always required before hybridization? Our answer will be no. And to explain the answer, we examine the structure of the ammonium molecule. For the isolated nitrogen atom, we see the 2s orbital with an electron pair and all 2p orbitals with single electron. As can be seen, for the formation of 3 NH bonds, there are 3 single electron orbitals in the p orbitals of the nitrogen, and so nitrogen does not need to be excited before hybridization. In the following, 1s and all 3 p orbitals of the nitrogen atoms mix together and form 4 sp3 hybrid orbitals that one of them with the electron pair which does not participate in the formation of the NH bonds, and the other 3 sp3 hybrid orbitals participate with a single electron in the formation of the NH bonds. In the ammonia, the lone pair on the nitrogen atom creates a great repulsion on the bonding electrons of NH bonds and decreases the bond angle from 109.5 degree to 107.5 degree. We know that in each sp3 hybridization with 109.5 degree angle, the participation percentage of s orbital is 25 and p orbital is 75. Based on this fact, the sum of this percentages all for sp3 hybrid orbitals is equal 100, and the sum of p percentage is equal to 300. Regarding to the bond angles of 107.5 degree in ammonia in H3 molecule, and with the using of the Drago rule, the actual percentage of s orbital in NH hybrid orbital obtained 23. Then with using the above equation, the actual value of the s orbital percentage in the lone pair hybrid orbitals obtained 31. For the phosphine and arsine, the observed bond angles are 93.5 degree and 91.8 degree, and by using the Drago rule, this percentage can be obtained for the phosphine lone pair of 82.7, and for the arsine is 91. Maybe there is a very logical reason why NH4 plus is formed easily, but the formation of PH4 plus is very difficult. According to the energy exchanges of atomic orbitals in a group of the main elements of the periodic table, from top to bottom, the tendency of perform hybridization is greatly reduced, and practically hybridization is not performed for the third and fourth rows of the main elements of the periodic table. For example, about 142 kilocalorie per mole more energy is needed to hybridize the s and p orbitals of the isolated phosphorus atoms in the formation of phosphine. Rationalize the trigonal bipyramid shape of PCl5 molecule, and regarding to the electronic configuration of isolated phosphorus atom, it is clear that to form the PCl5, one electron of 3s orbital excited to one of the 3d orbitals of phosphorus atom, and in the following one 3s orbital, all 3p orbitals, and one of the d orbitals of the phosphorus atom mix together and form 5 sp3 3D hybrid orbitals which point to the vertices of the trigonal bipyramid. Yes, each hybrid orbital overlaps with the 3p orbitals of 5 chlorine atoms. It should be noted that although the hybridization is sp3d, but it will be considered as 3 sp2 hybrid orbitals on the equatorial and PD in axial position, and it will be not be correct to think that all 5 orbitals are the same. Geochemical shape of sulfur hexafluoride can be explained using a concept of hybridization. To form bonds with 6 fluorine atoms, sulfur needs 6 orbitals available for bonding. In this case, sulfur undergoes excitation and 1 electron of trace orbital and 1 electron of 3p orbitals were excited to the 2 3d orbitals of sulfur atoms. And in the following, 1 3s orbital, all 3p orbitals, and 2 3d orbitals of the sulfur atom mix together and form 6 sp3d2 hybrid orbitals, which point to the vertices of octahedron. And its hybrid orbital overlaps with the 3p orbital of 6 fluorine atoms. In general summary, the number of sigma bonds and lone pair located on the central atom determines the type of hybridization for us. For this purpose, we can easily use the following formula, and in this formula, sigma is the number of sigma bond, and caps like A equal to the number of valence shell electron of central atom, and caps like N equal to the number of lone pairs that's located on the central atom, and a small letter N equal to the number of atoms around the central atom, with the exception of oxygen and sulfur, and a small letter M equal to the charge of molecule. Now we will have some example, IBr2 plus and SF4. To determine the structure of this molecule using above formula, we must determine A, N, and M. A is 7 for the iodine as central atom, N is 2 because of 2 bromides around the central atom, and M is +1. Now, I put numbers instead of parameters in the formula. Sigma plus N equal 7 plus 2 minus +1 over 2, that equal 4. According to the above table, the number 4 corresponds to sp3 hybridization. On the other hand, for this molecule, we have 2 sigma bonds because of 2 bromides and so 2 lone pairs. Of 4 available positions in sp3 hybridization, 2 are occupied by bromides and the other 2 by lone pairs. In another example, SF4, A is 6 for the sulfur as central atom, and N is 4 because of 4 fluorides around the central atom, and M is 0. Now, I put numbers instead of parameters in the formula. Sigma plus n equal 6 plus 4 over 2 equal 5. According to the above table, the number 5 corresponds to sp3d hybridization. On the other hand, for this molecule, we have 4 sigma bonds because of 4 fluorides and so 1 lone pair. Remember that in the trigonal bipyramid structures, the lone pairs must be in the equatorial position. Then, of the 5 available positions in the sp3d hybridization, the lone pair occupy one of equatorial position, and the remaining 4 positions will be filled by 4 fluorides.